All right, the next thing I'm going to talk about here is just basic thermite. If you know anything about the World Trade Center and you've been following it, you've probably heard the term thermite. All thermite is traditional thermite is aluminum, powder generally, and iron oxide. That's traditional thermite. It doesn't have to be just those two. You can do the same thing with aluminum and copper oxide. You can do the same thing with aluminum and molybdenum oxide. You can do the same thing with aluminum and a lot of other metallic oxides or oxides in general. But traditional thermite is iron and aluminum because it just works real well. And it produces molten iron. And traditionally it was used for things like welding railroad tracks. You know, when they would have two rails, they'd set up a crucible above that, and they'd put in thermite above it, they'd ignite it, and then they'd open a door below, and there'd be a little mold frame, and it would actually just let molten iron down in, weld the two tracks together, and then they'd grind it to final form. That was one of its earliest applications. One of its more traditional uses today is by the military. When they want to decommission a piece of artillery or any type of equipment, they take what's called a thermite grenade, and they'll send it down the barrel, in this case generally. It does not explode. It simply burns, produces a huge amount of heat, and produces molten iron, which melts again at 1538 centigrade, but it's also so hot that the aluminum oxide that gets formed as one of the other products, and we'll get into that a little bit, is also molten. And aluminum oxide doesn't melt until over 2000 degrees centigrade. This is incredibly energetic stuff. So when they drop it down there, what it does is it doesn't explode, but it just ignites, and it produces a blob of molten steel or iron that will actually melt through the steel barrel and basically decommission that tank. You can't fire it, at least not very well if it's got a big hole out the side of it. So the real key here to what makes thermite happen is we've got aluminum, and then we've got iron oxide. Again, you probably can't read this real well, but basically what happens is the aluminum loves the oxygen. It's a much stronger, I'll say, grabber of electrons, if you will, or giver up of electrons. It gives them up. But it basically steals the oxygen from the iron oxide. It takes it. It just literally goes in there. It's the bully on the block of the group. And he goes in there and he says, I want it, it's mine, and he takes it. And so the iron gets left alone, but along with that, there's a huge amount of energy release. You could think of it as a horrible fight, right? It's just this huge amount of energy that gets released, and everybody gets liquefied because of that. There's a little trick that you can play with thermite, and people have done it. And then instead of being called thermite, they call it thermate. And all they do is they add a little bit of sulfur. You still let the aluminum grab the oxygen from the iron, and he produces a huge amount of heat. But because you've got sulfur there now, it alloys in with the whole mixture, and it basically forms that iron-sulfur eutectic that I spoke about earlier, that has the ability to melt through the steel at much lower temperatures. And you can go do patent searches and put in thermite, thermate, building demolitions. There are patents. People make a living making various charges that have the ability to cut through steel beams.
Further information we get if we are applying this energy dispersive spectroscopy to such a cutout of the close-up of the red phase. This is an electron microscope. This picture shows where the iron is. This picture shows where the aluminum is, and where the oxygen is, where the silicon is, and where the carbon is. And there is some correlation. You can, for instance, see here that the aluminum is found in the same regions as the silicon, and we may already now get the impression or the idea, the information, that the aluminum and the silicon is located in these flat, what should we call, flakes, which is seen here from the side, actually, while the iron and the oxide is located here in these small particles. And that is what it is. I can tell you already now. This white particle here are iron oxide. Now, one very important point here is the aluminum bound to the silicon or isn't it? Because aluminum and silicon are very, very common elements in nature. It's so that the most common element on Earth is oxygen, number 2 is silicon, number 3 is aluminum, because they're omnipresent in stone, granite. But we did an experiment where we dropped one chip at a time into an organic solvent called methyl ethyl ketone. This, ladies, is almost the same as acetone, which you all know for removing of your nail polish, right? So let's say it's acetone. It would work the same thing, but we use methyl ethyl ketone because it has a higher boiling point. It's easier to work with. Now, if you drop one of these chips into methyl ethyl ketone, the red phase swells like a sponge. Like if you put a dry sponge in water, it swells almost 6 times. And this is what you see here from the side of the red layer. This is an electron microscope's picture of the swollen chip. And now we're applying the same technology. We are trying to map the chip according to elements. And the information you get here is that the aluminum distribution is now different from the silicon distribution, meaning that they cannot be bound together in a chemical substance. If they were, they would not be separated. Furthermore, if we apply this energy dispersive spectroscopy to a silicon-rich area like this one, we get a spectrum out like this, only silicon. Here, a little iron oxide, because you cannot expect it to be completely, of course you see a little iron also. And if you apply it in an area where there's only aluminum, like here, you see aluminum and very little silicon. This means that the silicon and the aluminum are separate entities, and the aluminum can move around as a consequence of the swelling with the methyl ethyl ketone. This is an indirect but a good proof of that we have the presence of elemental aluminum, which is very, very important. But it is not the strongest evidence we have. The strongest evidence we have comes from the reactivity of these chips. Just a second. That's better here. Because when you heat these chips up, they react. It's not easy to show, what we're aiming at now is, you should know, we are talking about nano-thermite, we're talking about the thermite reaction. You have seen this reaction scheme many times already. You've seen, and it was invented, thermite is a very old thing. It was invented by Hans Goldschmidt, a German chemist, in 1893. It was patented in 1898 and applied for the first time in 1899 for welding of tram rails in Essen in Germany, in the Ruhr area. Because in the thermite reaction, as you have already heard many times, you form elemental iron at a very high temperature. So it's very useful for welding. Now, but it can also be used to destruct things, which we have seen Jonathan Cole demonstrating so nicely. And this is the reaction which you would expect. Notice that we have seen there is in the red grade chips, there are iron oxide. We have seen this from the energy dispersive spectroscopy, and we have a good reason to expect elemental aluminum to be present. So wonder what happens when you heat them up.
What I did is I set up a little instrument where I could basically control heat these chips. And I basically made up a little apparatus with a stainless steel heating strip that I could electrically control and heat just to the point where these chips would ignite, because we know what their ignition temperature is based on other scientists' work. So I can basically, in a controlled manner, bring these chips up to the ignition temperature, watch them ignite with my microscope and camera, and you're about to see one, and then go in and analyze what's happened after the chemical reaction, and that's what you're going to see here. But basically what happened is that chip ignited. And what you see, and we can go, anybody that actually wants to see it, we can watch it on the laptop over there afterwards, and I'd welcome you to do that. But basically what you're going to see is, on the left-hand side of that chip, you're going to see a sudden bright flash. White-hot flash, and you're going to then see a wavefront move through the inside of the chip because it's so bright inside that it's actually radiating through the material that's still surrounding it. And you basically see a bright flash progressively move through that chip and then extinguish. So it moves from left to right and then extinguishes. And it's like, okay, it's not overly spectacular, but, something happened there. So this is basically that same chip afterwards, and it pretty much it puffed up, and you could see gas escaping from it. And so it's basically become porous on the outside with actually some holes that burst through for the gas to escape out. And that's just the other side of the chip, showing you again how it's been changed. What you find inside the chip after it burns, and what I'm pointing here, and you can't see them very well, but there's all these iron droplets now that have, from the reaction, have basically fallen to the bottom of the chip, and then when they cooled, they've solidified. So they're not perfect spheres. The spheres form, because we call them the microspheres, when a material is liquid and it falls through air, the only real force acting on it primarily is its own surface tension, and so it tries to minimize that surface area, actually, and hence the surface energy, and it goes into a sphere because that's the minimum surface area for a given volume of material, and so you wind up with a sphere. These don't form into perfect spheres. They're trying to, but when they hit something, they flatten out. But you basically wind up with all these metallic iron-based droplets that get formed inside the chip. And the other thing that they don't all form into droplets. The other interesting thing is as these are actually burning down through the chip or melting their way down through, they actually along the walls leave this very thin film of solidified iron. Whereas if you take these chips before you ignite them, and I've done it, just like I did where I said I exposed a fresh section, I've cut into these chips dozens, if not hundreds of times, and I've never found an iron microsphere inside. I've never found a film of iron inside. It's not there until the chip reacts. When the chip reacts, it produces molten iron, and you get that iron there. There's no iron, free iron. There's iron oxide before you ignite it. But there's no free iron inside these chips. It's only after it burns and it reacts that the thermite, it's the same in the thermite grenade. If you open up a thermite grenade, you're not going to find any iron inside. It's not there. It's all tied up in the iron oxide. But after it reacts, there's plenty of iron.